Hi, everyone. I'm Huining Li. I'm an assistant professor from North Carolina State University. Welcome to the last session in the afternoon. So since we have very tight timeline, so each presenter will have 8 to 9 minutes to present their paper. So first, let's welcome Jinsong Li to present the first paper.
Hi everyone. So thank you for the introduction. I am Jisung Lee. I'm from UC Berkeley, IOR Department, Industrial Engineering and Operations Research. I'm here to present my work on decision tree reinforcement learning for mechanical ventilation. This is a joint work with my advisor Anil Aswani and Professor Malini Mahendra from UCSF Bain Children's Hospital. As a brief introduction, mechanical ventilation is a critical life support intervention using a ventilator machine with the goal of delivering oxygen and taking out the carbon dioxide, which is basically why we breathe. In cases you would require this intervention would be cases like post-operative recovery or cases like severe lung injuries or diseases like COVID, pneumonia. The thing about mechanical ventilation is that this has to be done very carefully because improper administration of mechanical ventilation can come with ventilator-induced lung injuries, such as like when you choose like a too high of a fraction of inspired oxygen or too high of a tidal volume, leading to hyperoxia and other complications. So there is a need to continuously readjust the ventilator setting, depending on how the patient responds to the treatment and how the patient's condition evolves over time. So this is where reinforcement learning lends itself really well to this problem, because we have a very clearly defined state space, which would be the patient's physiological condition, and the action space would be what setting we choose on the ventilator machine, such as a tidal volume, fraction of inspired oxygen, or positive end expiratory pressure. And all of this interaction data, how the patient responds to a certain action, is very available at scale. Which allows for the training from large set of data sets to train a reinforcement learning policy. So we framed this mechanical ventilation control problem as an MDP, where the state space would be, as I said, the patient condition, the action would be the ventilator setting, and then the reward function will be defined in such a way that it reflects the patient's improvement in the health condition over time. And we'll get to this later. So the question I'm trying to answer here are three things. One is, okay, so how do you train a reinforcement, train an interpretable reinforcement learning policy? And in this project, it will come as a form of a decision tree. So more interpretable the policy is, the more shallow the tree is going to look. And hopefully this decision tree policy is also going to be outperforming the clinicians, at least what is seen on the data. And then the second question is, so when we have this policy, what's going to be the clinical implication of this? What the decision points, what the splitting points are telling us. And the third point is, how do you do the off-policy evaluation that enables us to validate that this policy is at least not doing terribly? I'll skip at the literature review for the sake of time. So I think it's more useful to talk about the data set first. So the data is collected from Mimic3 database. I think many of you will know this one. It's a large-scale open access database, including the patient stays in Beth Israel Deaconess Medical Center in Boston from 2001 to 2012 or 13, I believe. And from this database, I was able to retrieve about like 11,000 mechanical ventilation events or episodes after some appropriate pre-processing and removals. And so these are going to be the features that we collected and decided is going into this reinforcement learning problem. So they come in time series format, 5 of which are going to be non-time varying because they have to do with demographics. And so the first 3 bullet points, they will make up the state space, and the last one will be the what actually happened in history with the ventilator setting. So let's go over the MDP definition. First, we'll start with the reward function first. Sorry, let me check how much time. Okay, so we choose like a discount factor that's close to 1, but not exactly 1, because that's also standard, and it kind of reflects how the reality is with the mechanical ventilation, trying to not to elongate the mechanical ventilation too much because it's known to be harmful. So when we design this reward function, we take into account how the inherent goal of mechanical ventilation is to deliver oxygen, not to keep someone alive, which is what some of the literature have done before our approach. And it can be argued that the 95% of the blood oxygen level is a sufficient threshold for us to believe, okay, this patient is doing well enough. We don't want to pursue way above 95% at the cost of like choosing too aggressive ventilator setting. So we designed this reward so that it seeks for the improvement in the blood oxygen level, but it's going to have some constant coefficient being subtracted so that we also discourage it from choosing too aggressive settings too often. The action space, we assume that we're dealing with volume-controlled ventilation, which means that we are going to have 3 action dimensions, fraction of inspired oxygen, tidal volume, and positive and expiratory pressure. This has been split into 7, 4, and 7 bins after clustering analysis, and the tidal volume of level 6 and above, basically 6 and 7, and fraction of inspired oxygen of 4, 5, 6, and 7. Those are going to be considered aggressive actions. So the state space, we assume that for the oral agent, out of the 22 features that characterize a patient, 12 are going to be hidden from them, and only they get to use only 10 of them. And I will explain why we make this choice. So there was a very much difficulty trying to learn the transition dynamics of the patient. And this is due to the inherent complexity of the patient and the confounder that is not observed. So we take an approach that deals with this by assuming that there is some unobserved confounder in this setting, and then we make an assumption that we have a propensity to mortality that identify this confounder, and this propensity is going to be non-time varying, and this will be used as like a sort of a feature. So what we do is we train a logistic regression model to train 90 days mortality using the remaining 11 features that was chosen to be unobservable to the reinforcement learning agent. And this output from this logistic regression model served as a proxy of the confounder. And this will be employed in the later stages of policy training and evaluation. And then we construct this transition model using Nader-Watson estimator. Nader-Watson estimator is basically a nonlinear regression model that uses a kernel density estimate. I will skip the details. So using this transition model approximated by Nader-Watson estimator, when we do the off-policy evaluation, we roll out the trajectories by taking the initial state from a patient and then just roll out using treatment policies and then see how the policy does. For the policy itself, we choose 3. One is behavior clone, which is a supervised approach to mimic what the clinician has been doing in the data. And CQL, short for conservative Q learning, at the time of this project, it has been known as like a state-of-the-art deep reinforcement learning algorithm for offline learning. And it uses deep neural network, so it's not going to be interpretable at all. So you can see it as like a other end of the interpretability if you have choices over what kind of policies you're going to choose. And the last one, conservative queue improvement. This is going to be the decision tree policy that's able to learn in offline fashion as well. So that's the flow of the logic. Sorry, how much time do I have? 1 minute. So here I wanted to note the trade-off between the interpretability, model complexity, and the performance. And then obviously the deep learning one achieves a very good balance at the cost of the interpretability. I want to say if you go down to level depth of 5, it kind of recovers the performance kind of closely. And this is the last slide, so I'll be done really shortly. So that's the decision tree learned by the RL policy. So we can say that the tree is considering the interplay between like hemodynamical carbon dioxide level, oxygenation level of the patient by looking at the features that's being used in the splitting points. Yeah, I think I cannot go into more detail. I want to talk about what the decisions are made in this decision tree. Yeah, but anyways, I'll have to conclude here. Thank you for listening.
By the Dianchen. So since our time is very limited, please finish your presentation within 9 minutes.
Okay. So hello everyone, thanks for coming here. So today I'm gonna present our work about ethical AI for healthcare systems with an uncertainty-aware, fair, federated learning approach. So here's today's outline. I'm gonna start with the introduction and motivation and mainly talk about our proposed method. So here, this research is motivated by a need to develop ethical and reliable AI-based healthcare systems, particularly for the disease detection. And so these days, the federated learning has emerged as a promising approach, allowing multiple institutions or devices to collaboratively train models without sharing the patient's data. However, will the FL enables such like privacy-preserving model training, the medical data heterogeneity poses challenges to ensure the fair and accurate predictions across diverse populations. And also, so ensuring such uniform performance across the clients, which we call the group fairness or the client level fairness, is essential in the FL to prevent the disparities in the healthcare outcomes. So if any of you kind of worked with the fairness in the centralized setting, the definition might be like a little bit different. So, so to kind of address this fairness problem, here we proposed a UFair, which is to improve the disease prediction accuracy and also the fairness in the healthcare systems. And this fairness is ensure the maintaining the consistent performance across the clients while addressing the fairness threats. And we also evaluate this framework on the real-world healthcare data, applying the uncertainty-aware framework to the Alzheimer's disease detection. So for literature review, I just quickly go through this. So basically, we found there was limited research on addressing the client-level fairness for the healthcare systems with a real-world data set. And also, there was lack of comprehensive evaluation strategies and fairness metric used for when considering the fairness threats in the system. So here, we just kind of comes up with the method to address this problem. So before going to our method, here I would like to introduce a preliminary about evidential neural network. So since we want to leverage the uncertainty in the predictions, also like the models, here is how we quantify these uncertainties. So basically, an evidential neural network extends the traditional neural networks by modeling the uncertainty in the predictions. So basically, it replaces the last layer of this network from the softmax to the ReLU for the non-negative outputs. And then we can use such outputs to form an evidence vector. And this vector is kind of used to compute like different uncertainties. So we call this kind of way to call the subjective logic. And so another difference between these two networks is also their loss function. So here I put one for the yin training. So basically it just follows the standard like the squared arrow loss function. But here we just replace the original terms with the terms that in the subjective logic, make it more suitable for the yin training. And yeah, so as said before, in this research, we want to ensure the model performance of each client is uniformly distributed while maintaining high prediction accuracy. Because in the fairness research, a critical problem is the trade-off between the fairness and the accuracy. So here we want to maximize this fairness, but also maintain a certain level of the prediction accuracy. And then, yeah, so there are the basic components in the FL systems. Basically, we have multiple clients. In this case, are the hospitals. And these hospitals will have their own local data set and train the local models. And then they will just send the local models updates to a central server. The server just aggregates these parameters to update the global model. So our approach is kind of a method for this aggregation process to improve the fairness and accuracy after we update the global model. Yeah, so we also consider some fairness attacks. And in this case, we say the malicious updates can cause the performance gaps among the clients, violating the uniform local performance. So in this case, any attacks that can cause such influence, we call them fairness attacks. So here we consider Byzantine attack, which is to disrupt the training process by injecting the arbitrary metrics, and also the poisoning attacks, which just to compromise the local data sets. And we just want to see, in the presence of these attacks, whether our system can still perform well. And yeah, I don't think I have time for this. So here I just put a formal definition for the fairness we use in this work, and also some basic knowledge about the subject logic is how we form an opinion for each client and how we use the uncertainty here. Yeah, so I just talk about our algorithm here. So basically, when we quantify the uncertainty, we found the predictive task often face the conflicting client opinion problem. So which means given the same inputs, two clients can have the completely different prediction outcome about the same variable. So then we say these two clients have the high conflict. And this high conflict can lead to the difficulty in determining the best predictions or the fairness issues across the clients. So to solve this kind of problem, here we just propose a conflict measuring framework using the degree of conflict in the subjective logic. So basically, here the algorithm is basically follow the standard way to do the federated learning. But here, in the traditional approach, after the global model receives the local updates, it just take the average of these updates and to get the global model. But in our case, after we have the local updates, we're going to calculate this degree of conflict between each client and the global model. And then in the aggregation, we want to assign the clients with a higher conflict more weight. So in that way, we want to increase the impact of these high conflict clients in the global model to reduce the overall conflict in the system, so that we can improve the uniform performance, which is the fairness. And here just some equations about how we calculate this degree of conflict. This is also from the subjective logic. I just also skip this part. Yeah, I just here is just our experimental setup about our data set. So here we collect 3 real-world data sets about the Alzheimer's disease detection, and they are about the MRI scans. But for the first data set, it is pre-processed to the volume measurement. So this one is in the tabular format, and the other 2 remain in the image format. And here I just put some example about our data set. The upper table is kind of the tabular measurement, and also some MRI scans in the image. And yeah, and for the metrics for the evaluation here, we just have the prediction accuracy. And also we have 2 fairness metrics. The first one is called loss disparity, which computes the variance in the testing loss value across the clients. And the other one is the accuracy variance, measures the variance in the accuracy across the clients, which is want to in different dimensions to measure the fairness. And then for the comparison schemes, here we just collect all the fairness-aware FL in the current research area. And I think most of them are the loss-based approach. And here for some Q value-based, they kind of use the Q value to control the level of fairness. So it's kind of to deal with the trade-off problem between fairness and accuracy. Yeah, I don't think I have time for the results, but here I just want to mention like our method can perform like fast against the baseline method in both the IID settings and non-IID settings. So just skip. I will just skip all the sensitivity analysis part. Yeah, let's just go to the conclusion. So basically, our proposed method integrates the evidential neural network into the FL framework, offering the advantages of the uncertainty over the existing approaches. And our method outperforms other fairness-aware FL schemes on the healthcare dataset. And so in the future, for this work, we plan to extend by integrating the privacy-preserving techniques into the current framework to maintain both privacy and fairness while ensuring the high prediction accuracy. And also, we will also extend this work to handle the multimodal data for the improved performance and generalization in the healthcare scenarios. Yeah, that's it, I think.
Mira?
So hello everyone, my name is Mirza Farhan bin Tarek, and today I will be presenting our research work, Fairness Optimized Synthetic EHR Generation for Arbitrary Downstream Predictive Tasks. So the motivation behind this work was that even though EHRs or electronic health records are widely being used for clinical machine learning related tasks, the problem is that because of different privacy laws like HIPAA and GDPR, the amount of data that is available to the researchers is very limited. And to solve this, one solution could be to use synthetic data to increase the number of sample size available to the researchers. But we should also make sure that diverse subgroup representations are also conserved in the synthetic data. And so our main challenge here is to create synthetic EHRs that fairly represent real-world diversity. So that means that in the real world, how the distribution of different ethnic groups, different age groups are also preserved in the synthetic data that we have created. So before we go into the details, I will go through some backgrounds quickly. So EHRs or electronic health records are digital versions of a patient's medical history, and it's longitudinal. That means that there is a temporal aspect to it. And so then temporal data in the EHR consists of like lab events, and also there are physicians' documentation, medications, and treatments. And also it contains static data like the patient's demographic information, their name, age, and all of those information, and also their medical history. And as we are also dealing with fairness, so in the context of machine learning, fairness means that models should not discriminate against a certain subgroup of a sensitive attribute. And they also try to minimize bias towards protected subgroups. And there are different ways that we can measure fairness. And in our research, we mainly went with two types of metrics. One is called group fairness, which focuses on ensuring the performance of a machine learning model is equitable across different groups. So that means for a certain subgroup, so for a certain attribute like ethnicity or age group or age, in the different subgroups like different age groups or different ethnic groups, the machine learning let's say if we talk about predictions, is the predictions are equitable. And we can measure it using disparate impact, which compares the proportion of individuals that receive a positive output for two groups. And this proportion is should be closer to 1. So that means that the positive prediction for the unprivileged and the privileged group is almost equal. And there's another one that we focused on, which is called minimax fairness, which is an approach to fairness that aims to minimize the maximum disadvantage experienced by any group. And to measure this, we can use TPR or true positive rate parity, which requires that each group must have the same opportunity of being correctly classified as positive. And to mitigate bias, there are different techniques that are available, like pre-processing techniques. We work with the data itself before feeding it into the model, and then we have in-processing techniques, which kind of try to modify the model itself, and then we have post-processing techniques which are applied after the model. So our main hypothesis is that developing an end-to-end pipeline for augmenting real EHR data with fairness-optimized synthetic EHR data will improve fairness metrics in clinical downstream tasks and provide the researchers and clinicians with a larger data set. So by fairness optimized, we mean that we do some stuff with the generator, and after that, when we generate the new synthetic data and use it with the real-world EHR data, it should improve the downstream the fairness metrics in the downstream predictive tasks as well as the prediction performance. So there are some existing methods. I will go first with this. So we have generative adversarial networks, which has been used, but they are not state-of-the-art because they are not very good at generating synthetic data, which has temporal aspects. And then you have DDPMs, or denoising diffusion probabilistic models, but the one that we went with is large language models. So for example, we have hierarchical autoregressive language model that was proposed in 2023, which treats patient data generation as a language modeling problem. And then you have SEACH or GPT, which is a GPT-based model. But the problem is that they didn't focus on the fairness aspect of the generation pass. So that is why our main contribution here is to develop an end-to-end model agnostic pipeline for generating fairness-optimized EHR data by removing algorithmic bias from the generator itself using in-processing methods, and then we augment real EHR data with the generated synthetic data to improve fairness in downstream tasks. So downstream tasks can be like mortality prediction, length of stay predictions, all of those. So here is our proposed pipeline. I will go into the details here. So at first we do the usual pre-processing stuff, but we also extract patients' visits informations as well as their episode level information, so patient outcomes as well. And after that, we feed it to our main generator. So here we have used a modified version of the Halo EHR generator that was proposed by Theodore in 2023. So in here we have visit level modules, which has positional embeddings and code embeddings, and they are combined to get visit embeddings. So visit embeddings contain the visit data and also the medical codes, and they are then sent to the transformer decoder block to generate a sequence of visits. So after that visit level embedding is then the transformer decoder block's output is then sent to the code level module, which processes it to generate medical code probabilities, and these probabilities indicate the likelihood of various medical codes being present in each visit. So what we did here is that during the training time, in addition to the binary cross entropy loss function, we added another fairness loss. So that fairness loss is calculated during the initial training, and also we can feed it back from the downstream task as well. So here is our fairness optimization objective function. So here we have the model loss, and then we have the loss function here. So we have the binary cross entropy loss plus lambda LF. So LF here is the fairness loss that we initially calculate during the model generation, and this fairness loss can be the disparate impact or any other fairness metric, and we use that to generate initial data set. And after that, after using the generated data to do some downstream tasks, we can again do the calculations and get fairness metrics and use that again as a loss signal inside of the model itself. So that means we are kind of like doing a feedback loop. So from the downstream task, we are feeding back the loss function here. And this is what we call LDF, or the fairness loss from the downstream tasks. So we have done against our three baselines. So we have done the experiments with multiple types of data sets. So one here is the real only. It has only real data. We have real and oversampled data. So this oversampling is done using double prioritized bias correction method. And we have another data set, real plus SINT, which was in here. Real data was augmented using regular synthetic data, which has been generated using the Halo, but not the fairness optimized one. And in our experiments, we have used mimic3 EHR data, and as well as PIC or pediatric intensive care dataset. So I'll go through. So our downstream prediction task was mainly a mortality prediction task. So here we have our first experiment where we have calculated the disparate impact at the worst true positive rate and F1 score. So for example, in here we have 2500 real data and 2500 synthetic data. And for this, we have shown the disparate impacts and WTPR. So you can see that the worst true positive rate is quite high for our proposed method. But you can see that the F1 score is a bit low because we have observed that when you try to focus on the fairness aspect, it might hit the prediction performance as well. So there is a kind of trade-off. So here is another set of experiments, and we have also observed similar trend here. These are the experiments with the PIC dataset. And here's another example where we have changed the lambda values and we got similar results. So our main takeaway here is that including synthetic data can improve the fairness metric by sacrificing accuracy if we use our proposed method, and sample size plays an important role in the calculations. So that was for me. Thank you.
This is still on, no? This is still on.
Okay. Yeah. It's good now. It's good.
Good. Thank you. Okay. Thank you, everybody. I'm Shreyasi Das Bhattacharya. So this paper is essentially our students' paper. They are not here, so I'm just presenting on their behalf. I'll just quickly go through the motivation part of it. It's well known. Mental health is a global problem, and we have already talked about that's enough in this conference as well. While AI has demonstrated its significant promise in this field, intelligent care management, diagnostic of various mental health conditions, problems still persist. Real problems still persist. The first one is the objective of this work is continuous real-time mental health monitoring via wearable devices, right? Which might provide more personalized context that may help clinician offer more support, personalized support to ensure improved learning. The other problem that objective that we have in this work is generic. The model should be generic enough that can handle various practical challenges like sampling rate. You are getting multiple signals from multiple sensors, so sampling rate might be significantly different. Some of the sensors might not work at some point of time, missing data. Noise sensitivity. Many times, user might not want to wear it or might not wear it properly. So noise sensitivity and diverse multi-sensor signal. How do you combine them together to have a comprehensive decision making for any task, for that matter? So the problem is particularly complex due to various practical issues. The first one is data availability. First of all, unlike most of the standard computer vision related models where you just grab some videos and have some annotators to annotate it, right? But here you really want the users to wear those wearable devices, right? And you have to have users from diverse background, diverse health care related context. So it is not really that straightforward, right? So data availability is limited. Acquired signals from wearable devices might be as well very noisy or at some point of time completely missing, right? Finally, the intra-individual or inter-individual challenges, right? For example, the way person X reacts to a situation or expresses their emotional outburst or emotional state at a given point of time might be very different from another person, right? So all this combining together, how do you generalize this model so that whenever I have used 100 users to build our data set, and that model is ideally going to be useful for another set of 100 users, right? So these are some of the challenges that we are trying to address in this work. Our contribution is we propose GM FuseNet, that is Generalized Multi-Sensor Fusion Framework, and the main, I would say, main building block is going to be upon a very insightful cross-attention mechanism that is not just effective but also efficient and scalable to address long-range dependency information and complex signal-to-signal, intra-signal, or rather inter-signal information context. An effective preface multimodal transformer module that works as the encoder, and finally, extensive evaluation. So this is the method overview. Don't get overwhelmed with the picture. So we will start very simple, just by animation, so that it doesn't overwhelm everybody. So our main encoder is the temporal convolution network that work as a task-agnostic encoder. And the preface transformer model, this is what typical layer of TCN looks like. And preface transformer provides in early fusion of sensor-specific signal encoders, and then we have this multimodal fusion that ideally works as a counterpart, decoding counterpart that works, that essentially ends up learning a set of query vector which are working on different parts of the input, so that a long-range dependency information can be captured by a bunch of, in fact, by an array of learned query vector. And this is what this multimodal fusion looks like. And end of the day, we just try to, we try to capture multiple mode-specific fused head, and we have a global classification multimodal head as well, which is used for classification. So I'll briefly go through each of the steps in a little bit in detail. So here we have the TCN. We have the TCN, and typically temporal convolution layer output looks like this. And the resulting encoder takes into consideration of two things. One, you have the position embedding, as well as you have a learnable latent vector, Fi, which ideally takes care of the learnable part of the input. And you next you have the preface multimodal transformer, which works as the multimodal encoder for our model, and that has that ideally has the that captures multiple part of the mode specific input and combines them together. And due to this option of having multiple different modes to be incorporated within the fused framework, it can as well mask some of the modes to handle missing modality scenario. The counterpart, that is the decoding framework, that is the multimodal fusion part, ends up learning a set of learnable vector, which will work as kind of specialized zone to take care of, to understand multiple parts of the input, so that long-range dependency information can be captured. And we use Zoro-like mask embedding techniques to ensure the model is essentially equipped enough to handle multiple missing modality scenarios. So the two temporal correlation, the entire model is trained end to end. So ideally, you have encoder and decoder, everything trained on end to end. And we have, these are the two loss functions that we will be using: temporal correlation loss and cross correlation loss. By having temporal correlation loss, we can explicitly take care of the temporal relation within as well as across mode-specific cues. The public dataly available dataset, VSAT and CASE dataset we have used for most of the experiments, and there we have, as you can see from the distribution of samples, there is a huge unbalanced issue, right? So that makes the datasets most challenging and interesting enough. And so this is what comparative performance looks like. GM FuseNet significantly outperforms most of the existing SOTA methods. And in fact, SSL being among the top performer of the baseline, there is a huge jump from this existing baseline, that is by about 2 to 4%. So the other experiment that we did to explicitly understand the missing modality scenario. So you ideally have multiple different signals coming from two different sensors. One is the Empatica V4, and the second one you have Raspberry Band. So we try to capture only a part of the signals and try to understand how the model reacts by having only part of the information available in the query time. Obviously, in the training scenario, you have a lot of flexibility. You can do whatever you want. So all the information that we are ensuring to be missed out only during the query time. So that was about the ablation study, including multiple missing modality scenario. The next one is understanding how the model performs in presence of noisy data. We have just used some Gaussian noises with some pre-specified standard deviation, and trying to observe the noise sensitivity part of it. And finally, this is the cross dataset generalization, where we believe that we might not always have enough money to have a huge data collection process to perform, right? So given this scenario, how can you best utilize your learned model to have it generalize in a new data environment? You might require some small amount of fine-tuning, but no extensive training. But here we haven't really done any fine-tuning. We have just used, we said, just different configurations of training and testing environment that we have simulated. Just one example, the first one uses, we said, E3 for training and case A3 as the testing, right? And we have compared this with the best performing baseline, that is SSL, and we can see that from the bar graphs, I think it's obvious that the more GM-FuseNet outperforms, right? So in conclusion, we present GM-FuseNet, generalized multi-sensor framework for emotion recognition exclusively from physiological signals. It captures, we have reported using accuracy and F1 score, and GM-FuseNet's ability to handle missing modality scenario seems to be robust, as well as cross dataset and cross task scenarios also makes questions.
The next speaker is Shanghao Shi.
Yeah, okay. Hello, everyone. Welcome to this presentation. So I'm honored to present our group's most recent research work, and the title of my presentation is MedLeak, Multimodal Medical Data Leakage in Secure Factory Learning with Scripted Models. So my name is Shanghao Shi, and I'm currently a PhD candidate in computer science at Virginia Tech. So the main focus of today's presentation is the federated learning. Currently, there have been many real federated learning applications. For example, Google is using the federated learning to train their next word prediction system. The NVIDIA is using actually the NVFlayer platform to enable more efficient distributed training process. And more importantly, in the healthcare domain, the Rhino healthcare platform is designed to enable multiple hospitals to collaboratively train the machine learning models, but without sharing their raw data. So in this context, because the federated learning do not need to share the raw data, it is considered to be a privacy-preserving mechanism. So compared to the centralized learning paradigm, which actually required all the clients to send their data to a combined data set before they can proceed with the training process. So this federated learning mechanism is different. So for the federated learning mechanism, all the clients, they actually train their local models on their local data set, and then they just send their model updates to the central parameter server. And this central parameter server will aggregate all the local models before it do the next training round. So within this framework, no local data is shared. However, for today's presentation, we are going to investigate one fundamental property of the federated learning system. It is the privacy concern for it. So we are going to answer, actually, can the federated learning system actually preserve our data privacy? And unfortunately, the answer is no. Let's have a recap for the federated learning paradigm. So during the training mechanism, the global model and the individual model updates are exposed to the attackers. And the question is, can the attacker actually retrieve any meaningful information just from this, the exposed information? And there have already been two types of the state-of-the-art privacy attacks, including the membership inference attack and the model inversion attack. So this membership inference attack aims to infer whether certain samples belongs to certain clients. And for this work, we are going to focus on the model inversion attack, which aims to reverse your shared information, the shared model updates back to your local training samples. And there are also some defense mechanisms, such as differential privacy just for the membership inference attack, and the secure aggregation for the model inversion attack. And for this work, we are investigating this model inversion attack. So we assume this attack is launched by the parameter server, which is really curious about the different clients' local training data. And they assume that the system is defended by the state-of-the-art cryptographic-based secure aggregation mechanism. And with this defense mechanism in place, the individual model updates is hidden. And from the attacker's perspective, only the global model and also the aggregated model update instead of individual one is accessible to the attackers. And the goal of the attacker is to reverse this aggregated model update back to the local training samples. So how to achieve this? We are going to introduce two extra attack components before the original global model sent to the clients. So the first one is called this linear leakage attack module. So this module can actually reconstruct its inputs from the gradients. It's pretty much powerful. And it actually needs knowledge about the target's data distribution, and unfortunately, this can be estimated by an auxiliary data set. So I have drawn a figure over here. You can see that for this attack module, the attacker needs to craft a two linear layer architecture. And the fundamental idea for this attack module is to reconstruct one sample on one neuron. For example, the first image is reconstructed almost perfectly on the second neuron. With this very good reconstruction module, we can have this fundamental idea for how to do the model crafting attack. So supposedly we have a model like this, and if we just insert this attack module in front of the original model architecture, and during the federated learning training process, when the gradients is provided to the attack module, the attacker can do the sample reconstruction. Right? This is because the input to this attack module is the same as the input to the whole model. However, we also need to address the second challenge. So it is like, can the attacker actually launch the targeted attack? So this is because in many scenarios, the attacker may only be curious about certain victim clients. And to achieve this, we are using the second attack module, named the zero gradient. So this zero gradient attack module actually leverages the mathematical property of this ReLU activation function. So this is pretty common in the machine learning models. And so the fundamental idea is that for the ReLU activation function, its gradient is always zero when the input is smaller than zero. So we can actually force the width and bias of the previous layer to be negative, so that the gradients of the other clients are always zero. So in general, we insert this linear leakage in front of the victim, so the attacker can do reconstruction over this victim. And for the others, we insert this zero gradient module. And because their gradients are always zero, we cannot reconstruct anything. This can help us achieve the targeted attack. So in general, this is the attack flow of our mechanism. So it's a two-phase attack. Phase 1 is conducted purely on the server side, and for the phase 2, it is conducted between the server and the clients. So in the phase 1, the purpose is to craft the craft the adversarial global models before they are sent to the clients. So for the victim client, we will send this linear leakage plus the global model, and for the others, we will send this their gradient plus the original models. And for the attack phase 2, when all the clients they have received the adversarially crafted global models, they will do their local trainings based on their local data sets. And after they do their training, they will send their model updates back to the server again, according to the normal federated learning routine. And because we are assuming the secure aggregation is in place, the attacker can only get access to this aggregated model updates, not individual one. However, this is enough for us to perform the attack phase 2, in which we can further reverse the aggregated model updates back to the local training samples. So regarding the experiments, we actually have implemented our attack on both the medical image and medical text dataset under different settings. We are using the commonly used evaluation metrics such as the PSNR score, which higher indicates better reconstruction, the SSIM score, which is a value between 0 to 1, and when your value is close to 1, it means that you are having a perfect reconstruction. And we are also using the attack successful rate and the attack time as an evaluation metric. Here are one batch of reconstruct samples. Maybe you have seen this in the panel discussion phase. So we select 36 images from the brain tumor dataset. Left side is original ones, right side are the reconstructed one. And in this case, 34 out of 36 images were successfully reconstructed. And here are also some numerical results. So let me just quick summarize this. So if you just check the last column, you can find that our tag can reconstruct hundreds of samples simultaneously with pretty good performance. And the tag can be accomplished within just a few seconds. This shows that our tag is very efficient. We also perform downstream tags on both the actual and reconstructed images, and we find that they have the same performance. And also we do the reconstruction on the medical text because the text samples also contains a huge amount of personal records, and you can find that the original ones and the reconstructed one, they are pretty much the same, and we also get very good numerical performance. So in summary, we have proposed a novel model immersion attack that actually challenges the fundamental privacy-preserving property of the federated learning systems. So this attack can efficiently and accurately reconstruct the site-specific medical images and text records. And we also show that the existing defense mechanisms are ineffective against our method. So this work is a joint work between the Virginia Tech and the Children's National Hospital. And this is the end of my presentation. Thank you very much.
Thanks for the nice presentation. Our last but not least presenter is Magna.
Good afternoon, everyone. I'm Meghna, and I'm a grad student from Purdue University. And today I'm going to present about how we can use interpretable machine learning to predict and understand mental health in college students. So this is a collaborative effort with Professor Shreyas, Wei, Ishwe, and Professor E, the PI of this project. They're all sitting here. So let's begin. As we see here, mental health in college campuses is no longer just a concern. It's a full-blown crisis. You can see here that nearly 3 out of 4 college students report mental health challenges. But despite this awareness, most interventions still come after the student is already in distress. So here's the question. Can we predict mental health status before it's too late? Well, of course we can. With all the sensing data we can collect today, machine learning can definitely help in prediction. But there are challenges. The first one, insufficient data. We do not have a lot of long-term data collected, and this limits our ability to track daily behaviors of college students that actually cause mental health issues. Secondly, machine learning models are often black boxes. That means they're not very interpretable. And without this interpretability, it's kind of difficult to use them in practice. Thirdly, most systems are not personalized. They generalize across students, but they kind of miss individual variation. Our solution, I hope, an interpretable hierarchical model for personalized mental health prediction is designed to directly address these three challenges. Let's go over all of them one by one. First, the challenge of insufficient data. We solve this by using a longitudinal real-world passive sensing dataset, the college experience study dataset. It was released in October 2024, and it has data of over 200 college students from Dartmouth, and the data was collected over 5 years. It includes over 172 behavioral features, including sleep patterns, location, phone usage, even conversation detection. And in addition to that, students also had to fill out weekly EMA surveys, the ecological momentary assessment, and this gave us insights to their stress levels, PHQ-4 score, social well-being. Let me pause for a second and talk about the PHQ-4 score, because this is what we use to predict in IHOPE. So the PHQ-4 score is a clinically validated standardized survey that screens for both anxiety and depression. So based on the total score, students are classified into 4 categories: normal mental health, mild, moderate, and severe. And when we combine this data with the day-to-day activities, we can actually start to analyze how a student's behavior might relate to their mental health status. The next challenge about the black box ML is solved by using interpretable models. So the core structure of IHOPE includes a 2-stage hierarchical architecture. We first map raw behavioral features from the CES dataset into manually crafted interaction labels that are just easier to understand. Then we use a neural network to predict the PHQ-4 category. So this structure gives us 3 advantages: the dimensionality reduction, interpretability, and a strong predictive performance. We'll see that in the upcoming slides. So let's talk about stage 1 first. So here we handpick certain relevant features from the CES dataset, do some feature engineering, and group them into 5 interpretable interaction labels: leisure, me time, phone time, sleep, and social time. So this step acts as dimensionality reduction, and also, it helps the model output more meaningful. So now these labels need to be quantified so that we can do machine learning analysis. So we use a rule-based scoring to convert this to numeric values. So these numeric values basically reflect personalized feature importance based on every student. For example, if we talk about sleep score, if a student is physically still or spends more time in their dorm at night or uses their phone less at night, we have a better sleep score. Right. Then in the final stage, that's stage 2, we feed these scores into a neural network with 3 hidden layers, and it's customized per student. The model then predicts the PHQ-4 category into where the student falls: normal, mild, moderate, or severe. The third and final challenge of limited personalization is solved by using personalized prediction. The reason why we need personalized prediction is because one model cannot fit all. Mental health pattern varies among students, among people, and we've seen that in previous presentations as well. For one student, running might improve their mental health, but for someone else, like me, it may be rock climbing. So even if my running time is close to 0, my mental health status still may be good because my rock climbing time is not 0. So to get this right, we need to capture individualized feature importance. And this is how we can make meaningful and accurate predictions. We'll see that it actually works. Now we'll go on to the evaluation of I-HOPE. For this, we asked 3 main research questions. 1, about its accuracy. 2nd, about interpretability. And 3rd, about individual feature contribution. So to answer the first question, we compared I-HOPE against 3 baselines. The first one is a standard aggregate model that is trained across all students. It reached around a 60% accuracy. The second is a personalized model. So we trained models for each student and then took an average, and we got around 70%. In the third baseline, what we did is that we first selected the top 50 features from the overall student population, and then trained personalized models for these 50% of these features. And this brought the performance down to 65%. The reason is because of the running, rock climbing example I just gave earlier. And finally, with I-HOPE, we get a 91% accuracy on average. Now let's turn to our second and third research question about interpretability and individual feature contribution. So to explore this, we analyzed the interaction label importance across students. So on the x-axis here, you can see that we have the student population. And on the y-axis, we list the different types of interaction labels. And the color represents the importance. The warmer color represents more importance. So what stands out here is that no single label dominates across all students. Let's take a random example. Like over here, you see that for one student, phone time is more important, and for another, it's social time. So this kind of insight gives us interpretability and helps guide personalized recommendations. And even within a single label, specific features have different importance for different students. And I-HOPE captures both these critical layers. Finally, to wrap it up, I-HOPE is the first interpretable hierarchical model for personalized mental health prediction for college students. The design isn't just elegant, it actually works. We see a 30% improvement in, for over baselines. But most importantly, it gives us a window into each student's behavioral world, what really matters for their mental well-being. So finally, just to conclude, I'd like to say that if we want machine learning to support real well-being, it has to be interpretable and personalized. And that's what we tried to do here. And we're excited about where this goes next. Thank you.